Yeah, so in the off, there is one important step. Once we generate the executable, in order for us to be able to run it on the Amazon F1 instance, we have to create an AFI, Amazon FPGA instance or image, FPGA image. There is some problem in that step yesterday when I tried, and Amazon people, and they're trying to fix that. But once that step gets cleared, then so you should you should try that also. And the things that you need to do for it are there in the second tutorial on the Vitis. There are two Vitis intro tutorials. Let me share my screen now. Yeah, so as you can see, so introduction to this Vitis intro 1. So these two tutorials you should all do. Vitis intro 1. So Vitis intro 1, we are all, that's what we are supposed to do now. And Vitis intro 2 is, we should, in Vitis intro 1, we did software emulation. In Vitis intro 2, we do hardware emulation, followed by actually running the design on the F1 instance. In the third step, when we want to run the design on the F1 instance, we have to create AFI. There is one small technical problem, not from our side, that I think some permissions needs to be enabled, I guess. It will be fixed. But till hardware emulation, you should be able to do with the current setting without any problem. So I strongly encourage you to do till hardware emulation. Software emulation, hardware emulation, you should do till now. And Tanmay has a question that I know in the video recording, when we start Vitis analyzer, there is a resolution problem. Because of that, it doesn't, it's not showing up. So when you launch Remina, so there is one color option or something like that is there. So there you have to pick true color 24 bits. Because apparently there is some problem with 32 bits representation of color. So yeah, color depth setting, Aryan has it. Yeah, so color depth setting, you can change it even to 24 also. I tried it with 24, it worked well. Okay, you can even change it to 16. Yeah, great. So yeah, so here again, so please software emulation in tutorial 1, you should do, because I am seeing only 50% of the class did. Hardware emulation, these two, you should finish by this weekend. Third is actual hardware execution. For the actual hardware execution, we need you can compile actually. In terms of compilation, it will take a couple of hours. Actually, you should do the compilation. Go ahead and compile. But from compilation to the next step, to the execution of the design, so we need to do something in between there. Yeah, you may have to wait for some instructions from my side. So go ahead with compilation. And then the next step, wait for it. Okay, so this you should do. And this will take a couple of hours. This will take a couple of 1.5 hours or something like that it will take. One suggestion that I have is, those of you by chance, if you have access to a machine with 32 GB RAM, at least 32 GB RAM is good enough. Then till the step 1, step 2, step 3, you should be able to do it on your local machine without any problem. Only the last step when you want to actually run it on the FPGA, then you can no, you can the XCL bin file and executables. Yeah, so maybe at least these two steps you can do on your local machine. The actual hardware compilation and those steps, you can do on the Amazon instance. That way you can save some credits. But no, the hard disk requirement to install Vitis is substantial, and the memory requirement is around 32 GB. So
Sir,
for
one question. So is that 32 GB is for the RAM?
yeah, 32 GB RAM. Yeah, that kind of
Because
works with all your laptops. Yeah.
I tried installing that Vitis the SDK.
Hmm.
Yeah, it is taking a lot of like almost 170 or 180 GB of the space.
Yeah.
But will it work if we have like a lesser RAM than 32 GB, like 8 GB or 16 GB maybe?
8 GB, I'm very doubtful. Maybe 16 GB you should try, but 32 GB is safe, definitely. The
Okay.
machine that we are using on Amazon, it has 32 GB RAM.
Okay. So
Yeah.
just one more question. If we have this local SDK, so we will be needing another license file for that, right?
No, no, no,
Yes.
or not necessary.
Okay.
Yeah. So Aditya, when you install Vitis by choosing appropriate options, the hard disk requirement could come down to around 80 GB or
Oh,
yeah.
I don't
So,
know what are those. So maybe
yeah,
I'll after this call I'll try to get in touch with you and
yeah.
I'll try.
From what I heard, no, there is one component of Vitis is uh, AI. If you remove AI, I think you should be able to do it in 80 GB, I guess, because the image, the army image is less than 80 GB that we are
Okay.
using. Okay. But
So
one
by
of,
default, there are a couple of options selected. White is HLS and Vivado. So so those three are by default. There are other external devices which are getting added. So like an engineering devices and all those stuff. So everything comes out to be 170 or 180 GB.
yeah, but I think what this case is, for most of you, you may not be able to do it, no, that kind of hard disk space. Hard disk you may have, but the memory. So Mohit, you just, all of us know the default is use the Amazon server, the AWS. Those of you who have capacity, a good workstation, you can try it. Meanwhile, we are also trying to see within the campus if we can have a server, this software installed on a server and do an RDP. But the problem is it's not going to scale because if many of you launch Vitis on that machine is going to crash. I'm not sure if we can facilitate that. So anyway, so yeah, this suggestion is for those of you who have a good workstation. You can do it, but otherwise, with $100 credit, 1 hour of workstation usage, the machine usage, it is 30 cents, it seems. So with $1, 3 hours with so you will have good amount of hours available uh, on the AWS itself. But having said it, still, if the facility is there, please go ahead and try to use. Okay. So now we will see what we will go through the add that vector addition code. So what is the vector addition problem? The vector addition problem, let me share my visual code. Yeah. So if you see in the Vitis IDE, it could be a bit confusing, but the problem that we are trying to solve is simple. Let me close this. So, but the problem that we are trying to solve is very simple. We just want to add two vectors. Okay, so a of no, whatever a of 1 to n is equal to b of 1 to n. So this is a plain vector addition problem. This is what we are looking at. And as you know, so the way these things work, we have the CPU, and the CPU has its own memory, host memory. This is what we call as CPU memory. This is host memory. And then we have an accelerator. Okay, so and then so this is an FPGA or GPU. Okay, this has its own memory. So this is device memory. And then what happens is, when we want to do computation, so data gets moved from the host memory to device memory. This is PCI Express bus. So data gets moved from host memory to the device memory. And we do some computation on the device on and then we initiate the computation on the FPGA. And then after the computation is over, we move the output back from device memory to the host memory. That is the setup. Usually what happens is, the accelerators themselves, they have some on-chip memory. In the case of FPGA, this is called as VRAM. In the case of GPU, it is called as shared memory, or I forgot its exact name, something called as shared memory. And usually this is called as global memory. When we say global memory, so it is called as global memory in the context of GPUs because that memory is accessible across multiple compute units that are present on the GPU. In the case of FPGAs also, we can just call it as all the circuits that are present on the FPGA have access to this global memory. Okay, and then there is an on-chip memory called, depending upon the device, we call it as VRAM or something else. So when we want to do, so on-chip memory is much more faster when compared to global memory. So you want to move data from the global memory to, I will rephrase it. So when we are doing computations, we would like to minimize the traffic, minimize the memory traffic between FPGA or this accelerator to device. We would like to minimize. And all the hard work that you will do in this course or not in any design is on how do we minimize this data accesses or memory accesses to the global memory. So that's where all the hard work goes. So what I will show you is I will show you first one CUDA code, and then for vector addition. You don't need to understand the details, but if you understand the code template, that is good enough. Okay, and then we will see.
Sir, excuse me 1 second. Did you say how to terminate the instance or to stop the instance?
Stop.
Okay.
You should not terminate.
Okay, we
If
have
you
to
terminate,
stop.
what happens is all the things that you have on your hard disk, let's say you have some files, everything will be gone there. It is destroyed.
Okay.
Yeah.
So I have to stop the instance.
Stop the instance, yes.
Okay, thank you.
So this is.
Sir, when we are stopping the instance, should we sign out also, or we can keep it signed in?
You sign out, but I don't think any reason why if you don't sign out, no, it shouldn't cost you. But Yeah, but the suggested thing is to sign out, to do 3 sign outs. The first sign out is from AWS, the second sign out is from Vocarium, the third sign out is from AWS Educate.
Okay.
But whatever worth it is, please do these 3 sign outs, because I don't know, what costs, if it costs anything. It should not cost once the instance is stopped, but I don't know. Okay.
Sir, and do you know the session time? Like, is it 1 hour, 2 hours, or like that?
See first. Okay, I will take these questions. We are thinking about one particular idea. In the middle of it, you are asking questions about logistics. I'll take those questions later, but the quick answer to this is there is no session duration, but the session can be 3 hours, 4 hours, 5 hours, but you will be charged. Okay, no more questions on this case. We'll take these questions at the end. Okay, so here, so this is this code that I'm showing you. This is not for FPGA. This is for GPU. Okay, I wanted to show this code for a reason. Okay, so here you can see there is this main function. This main function, this runs on the host. There is a CPU. This runs on the host CPU. This runs on the host CPU. And you can see we are allocating 3 vectors, A, B, C, and actually we are allocating 4 vectors. I think the 4th vector is for some other purpose, for some check purpose, I guess. So here you can see, so on line number 26. So when we do an malloc, the memory gets allocated on the host CPU's memory, on the host CPU's memory, DRAM, it gets allocated. That's what is happening on line 26 to 28. And so there is some other code. So on line 35 to 36, we are just initializing the 2 vectors A and B, the input vectors, which we would like to add them up. Dummy initialization we are doing. And so this line 38 to 40, they are important. So when we are programming a GPU using the CUDA programming framework, we use CUDA malloc function. The CUDA malloc function, it allocates memory on the device, on the global memory of the device. Remember, so every device it will have a global memory. So this allocates memory on the global memory of the device. And then the line number 42 and 43. So there we are doing a memory copy. We are transferring the vector A that is present in the in the host CPU's the host machine's memory to the device global memory, and A is a pointer. So if you go back and look at this picture, so this is the CPU, and this is the memory, and this is in this case it is GPU, and this is the GPU memory. So the pointer A, it points to the first memory location on the base address of the vector A in the host, and A underscore D A underscore D, it points to the base address of the vector in the GPU in the device memory. And we are doing a memcopy host to device. We are doing a memcopy host to device. That is what is happening here. So after we do the data transfer, we are transferring both the vectors A and B to the device memory. And then, so on line number 46, we are launching the kernel. This kernel gets executed. We are launching the kernel on line number 46. This kernel gets executed on the GPU. And after the kernel execution is over, you can see on line number 44 and 48, we are taking a timestamp just to kind of check how much time we are spending in the kernel. Okay. Anyway, that's a side note. And after the, so this line number 51, it's a vector addition on the host. It's just a function call. There is nothing. I think there in this particular program, they want to compare the time taken to perform addition of the two vectors when you do it on GPU versus on CPU. So you'll just ignore it. But line number 55, if you see, this is the place where no, the computation is over. And so we are transferring the data back from the device to the host. And after the data is transferred from the device to the host, we are freeing the memory that is allocated on the device using CUDA free library calls. So transfer data from the vectors A and B from CPU memory to GPU memory, perform addition, launch a kernel which perform the vector addition. The resulting the result will be available on the device memory, and then you transfer the data back to CPU. This is the template. This is the template. And if you see here, let's go and see in this particular case, unlike in the FPGA program that you have seen, where the kernel is in a different file, here the kernel is in the same file. And line number 8 to 12 is the kernel. You can see there is no for loop here. Usually when we want to do addition, you want to, there will be a for loop. But here, let's not get into the semantics of GPU execution. But roughly speaking, the ith element addition is done by ith thread. Let's say if there are 1000 element, if the vectors are of size 1000 elements, then what happens is there are 1000 threads, and every thread will kind of add the ith element of thread I will add the ith element of A with the ith element of B. Okay. So anyway, so this is, don't try to understand the kernel, but just giving a kind of idea. In this case, you didn't see a loop, you might be surprised, but there is a reason for it. Contrary, but on the contrary, line 14 to 18, this is how we do vector addition on your CPU, so you can see it. So keep this thing in mind. So one observation that I would like you to make is this whole program is written using CUDA library. So CUDA framework. So that means you will be able to run this program only on NVIDIA GPUs. Only NVIDIA GPUs. You will not be able to run this on a AMD GPU or Intel GPU. So yeah, you are bound to NVIDIA. So in order to, that means your software is not portable. When you kind of say, hey, I want to build software in C++, portability is one of the things that you have in mind. But here, portability is not, when you write things in CUDA, you are bound to NVIDIA GPUs. You are bound to a vendor. So there is work in this space in order to kind of come up with a avoid this vendor binding. So we have what is called as a OpenCL framework. It's an open standard. So if you write, you can write your same program using OpenCL, and if you write your program in OpenCL, you should be able to run it both on an NVIDIA GPU or AMD GPU or some other company's GPU or maybe Intel has some GPU, you should be able to run it if you write it in OpenC. Needless to say, while technically you might be able to run it on different GPUs, in terms of performance, no, it may not depend. As we move from one GPU to another GPU, the architecture differs. So you may have to re-architect your code or kind of engineer your code again, so that you can get the best performance out from a new GPU you are working with. And also one interesting thing is supposedly not only GPU, like if you write it in OpenCL, so you should even be able to run it, the same OpenCL code on a Xilinx FPGA, technically speaking, if you write it in OpenCL. But I'm not sure how much it is feasible and all. Okay, so now, so any questions here? They're all doing good so far? Are you getting any noise from the side? Suddenly the AC started without my switching it on.
No, sir, there's no noise.
No? Okay, great. Thank you.
Sir, in this kernel code,
Hmm.
that block IDX, block dim, where are they, like, from where did they come? Like,
No, don't worry about it. They are defined as a part of the in CUDA.h.
CUDA.h, okay.
Okay. So now So now let's look at our own code. That is the code which you are working with in the tutorial, and see how it looks like. So let me. So if you see the IDE, it's all like could look confusing. Just give me 1 minute. Some problem. Here my drawings maybe. Yeah. Here my drawings. So yeah, the IDE has so many things, but here I would like you to focus on XCL2. These are the 4 source files that are there. XCL2.cpp and XCL2.hpp, they are support files. So you focus on, you don't need to pay attention to them, but you may want to take a look at it. So one thing I want you to keep in mind is, so the code that is, so there is this OpenCL, so Xilinx OpenCL library that is there, but apparently this is wrapped to the, there are C++ wrappers provided for this OpenCL library, and the code that is written in these files is using these C++ wrappers. You are not seeing directly the OpenCL standard functions that you expect. You are working with C++ wrappers. Keep this in mind. So now let's go. So this is the main function. So in the main function, so there is lot of yeah. So there is one thing I would like to, we will revisit maybe at the end, or yeah, maybe we can, I can tell at this time itself. Let's say after you compile this .cpp file, an executable v-add gets generated. So to this executable, you need to give an XCL bin file. That XCL bin file is something that is obtained by compiling your kernel code. Okay, so you have to give this. Let's say, let's call it as v-add underscore kernel dot XCL. So this XCL bin file, so it is, we should pass it as a parameter to this host code. So host executable. VRD is the host executable. So, and that's what you are seeing on line 72. If you have less than 2 arguments, let's say, then it says along with the program executing, pass the XCL bin file, and then you have to specify the number of elements you want to add. Like if you don't give any parameter after this, it assumes 4096 as the default size of the vector. But otherwise, you can, if you are testing out how this code kind of works as you increase the number of the size of the vector, this is how you can do it. You can try out for 1 lakh elements and see how this whole thing works. Okay. Yeah, so keep this in mind. So this is the host executable, and this is the bin file that got generated from kernel. This is host executable. So you can see this is the default number, and you are storing the bin file in this binary file variable. Yeah, let's keep going. So I will not go through the details further. But roughly speaking, the story from here, I want you to go through this code carefully, for you to go through this code carefully. From line number 80 to 96, roughly what is happening is, the code is checking whether no, everything is set, and we should give XCL bin and the number of elements. If the number of elements are not given, it uses 4096. Okay, and then it checks if it's, yeah. So I will just keep skip all these things, and I will come here. So this is the place, line number 118 to 121. They are important because so there we are trying to allocate a vectors the memory. So just like malloc. So instead of using malloc, we want to use aligned underscore allocator, because we want the vector address to be a multiple of, I think, 4096. It should be, that is, when we divide it by 4096, then it should become, the remainder should be equal to 0. That is because I think 4K is the page size or something like that. And that will kind of boost up the performance, or I'm not sure about it. But when we use this particular aligned allocator, what happens is the address that gets generated, it is aligned on and a multiple of 4096 value. So this is memory array declaration part. And then these are all OpenCL things. So there is in OpenCL, we need to have a device, we need to have a context, and there's a command queue, and there's a program, and there's a kernel, and that's what is being declared on line number 125 to line number 129. And then on line number 134, so there is a search for devices. What are all the devices attached to my host? So you just make a call, and it tells all the devices that are attached to your host. And what happens here? Yeah. And this is where, so in this loop, we are looping through all the devices that are present. And the first valid device, I think that is present. So for every device, I think we are creating a context and a command queue, but you ignore the loop. And what is important is you are creating a context on line number 144. So you pick a device on line number 144, you create a context. That OCL underscore check, which is there now, it's a kind of a everything you put it under it, so that the error that gets generated when you make a call to context, I think if there is some error, it generates a good readable error onto the screen. It could be a macro OCL underscore check. Okay, similarly, on line number 145, what is happening is we are creating a command queue. We are creating a command queue, and then on line number 152, so here we are creating the program. I think we are flashing the program onto the FPGA, I guess, on line number 152, the kernel code. Okay. And then here, so we have this vectors underscore init function, which is a function that we have written where we kind of fill the buffer A and buffer B with random data. Like if you go 171, I'm going up here. Yeah, vector underscore init. We are filling up the vectors A and B with some random values. We are making the hardware results vector to 0 and software results to buffer A plus buffer B. The idea is later on, after we launch the FPGA instance, run it on the hardware, we want to compare the software results with the hardware results. And that's what we are doing in the verify. The verify, we call the verify function after we call the FPGA design. So the results from the FPGA design, that is hardware results, will be compared again as the software results. And yeah, so later on, I have an exercise for you. You may want to take the same program, I would like you to take, change the data type from int to float and see what happens. Int to float, to maybe even double, and change it and see what happens. If we are doing the addition of vector integers, but instead of, if you want to add the floating point numbers, what happens you should see. And you should pay particular attention to the verify function. Like whether the verify function passes when we move from the int data type to float data type or double float data. Okay. So let's come back here.
Hello, sir.
Yeah.
Sir, in this VAD.cpp, this thing is we are coding it for the CPU part, sir.
This is the
CPU part.
which one?
The VADD, this
Yeah,
code.
this .cpp, it is a CPU part. All this is happening on the CPU.
Then what's happening on the FPGA part?
Yeah, I will show you. We are not at here because so far, on line 170, we are at line 171. In line 171, we are just initializing the vectors.
In the CPU.
Vectors. On line 179, this is the place we are moving the data. Okay, we are moving the data from the host to device. Okay. So yeah, we just. So on line number 179, 183, 187, we are setting up things, and on line number 193 to 196 also, that's what we are doing. I think the actual data transfer is happening on line number 199, where we are migrating or moving the data to the device global memory. So this is all boilerplate code, but I want to, this is the most important thing. Let's say till this point, this is all boilerplate code. When you compare it with, the reason why I have shown you, the CUDA code is it is very easy to understand there. So there is a clear CUDA mem copy happening from the host to device very clearly. Here in this OpenCL code, it looks a bit convoluted, but this is all boilerplate code, but so just use it as it is. And you can slowly try to understand them as you try to do more and more involvement. But the primary thing here is on line number 199, the data transfer from the data to the device global memory is happening. And then on line number 204, so this is the place, so Kalesha, this is the place where we are launching the kernel, the vector addition module onto, which is already present on the FPGA. And then on line number 210, the data is moved from the device global memory to the host local memory on line number 210. This is what is happening on line number 210. Are you all with me here? So the most important things here is if you try to draw an analogy, this is step one. This is step one, where we move data from the move input data to the device global memory. And so this is these two steps, or you launch the kernel and you wait for the kernel to finish the operation. Computation is happening on the FPGA here. And then this is the step 3, where data is moved from this is device global memory to host local memory. This is step 3. This is what is happening. These are the exact steps. So I don't want you to get intimidated with a lot of code here. This is all boilerplate code, and you just use it as it is. And you can slowly try to understand what are the semantics of this method calls, and what are the parameters to this method calls, and how you can use them in different ways to suit your needs as you build more complex applications. Logically speaking, this is what we have here. And of course, if you go down, what happens is the result that you have obtained from the FPGA, you compare it on line number 260. This is what we to check if the hardware results match with the software results. Are you all with me so far? Yes? No? Maybe?
Yes, sir.
Great. So now let's take a look at the kernel code. So this is the kernel code. It has 3 parameters. It has 4 parameters, 2 input vectors, in1, in2, and out underscore r, it's an output. That's the vector to which we are writing the data to. And size indicates the size of the kernel. So line number V4, sorry. So line number 54 is important for you because, so here we are declaring a vector, and this vector, the memory for this is allocated, while in1, in2, out underscore r are present in the DDR RAM. So these 3 are present in the DDR RAM of the device. B1 underscore buffer, it is present in the BRAM. BRAM is an on-chip RAM of FPGA. So this is present on the, this is allocated on the BRAM of the FPGA. In the CUDA kernel that we have seen, in the kernel, if we have a declaration such as this, what happens is the memory for that will be allocated on the on-chip shared memory of the GPU. So I am trying to kind of bring out the analogy between GPUs and FPGAs here to the extent possible. The analogy doesn't carry all the way, but yeah. So this is what happens. So this is for a declaration here. This memory is allocated on the VRAM of the FPGA. Similar declaration in the context of GPU. it gets allocated on what is on the memory that is present on the GPU chip, not on the global DDR. And now, so if you see this code, okay, so if you check this code is the computation is happening in chunks. The computation is happening in chunks. So what we are doing initially here is, you can see here, there are two parts here in this code. In this first part, if this is your whole vector, this is your whole vector, then so what is happening here is this vector is divided into chunks of so you first bring this in this loop from 64 to 67, you are bringing in one. So in the first iteration of the outer loop, you bring this data and store it in the VRAM. And then what you do is in the code on from line 71 to 75, you are doing the actual computation. So one thing, if I am right, what is happening is this data access is coming from VRAM, whereas this into it, we are not buffering it on the chip, on the FPGA memory. So this access is coming from the DRAM. This is a DRAM read operation, and this is a DRAM write operation. DRAM. And when I say this is all device DRAM write operation. I hope I am right here. Okay, so but whereas V1 underscore buffer, this is a DRAM read operation. This is what this is. Okay, this is how the computation is happening. Maybe by doing this, like we can kind of, I'm not exactly sure the reason behind this, but this is a 101, no, the first base version of the code, but this is how the computation is happening. So in iteration 0, the first block of 4096 elements, the buffer size gets executed. The addition happens in iteration I1. The next chunk gets the next chunk of additions will happen, and iteration I2, so on and so forth. This is how the computation is happening. So in the case of, again, if you kind of look at this loop, the whole loop that you are seeing here, it gets this whole function or the loop that is present in this function, it gets synthesized into hardware. It gets synthesized into. Whereas in the case of GPU, this whatever the code that is present here, there is already a fixed circuit that is present on the GPU, and the instructions will be scheduled on them. But here, this circuit gets synthesized on FPGA. And you can keep on launching the so when you come back next time and run, so it is like this. So you have, in the case of GPU, you have a CPU and GPU is fixed. The underlying architecture of GPU is fixed. You try to schedule computations to get the best out of it. But here, what you are doing is you are synthesizing a custom circuit based on your kernel, and you are putting it on the FPGA, and then you are streaming in data and letting the kernel do its job. And it can only do this, and it cannot do anything else apart from this. Okay. So yeah, so this is the story, and of course we have to see how this loop gets mapped to a circuit. How this loop gets mapped to a circuit, and needless to say, your circuit is it's a fixed entity. So what has to happen is if this is your hardware that got synthesized, then across time, in the last class, we have studied folded combinational circuits, right? So what happens is, there will be some other control plane which kind of schedules different iterations of the loop across clock cycles on this hardware. Like in the first 100 clock cycles, iteration I1 will execute in the first 100 clock cycles, and in the iteration I1, will execute in the next 100 clock cycles. Okay, so maybe I will put a 0 to 99. So this from clock cycle 100 to 199. So iteration I1 will be scheduled on this hardware, and there will be a control plane sequencer circuit which schedules these iterations on the synthesizer hardware. And we will see in a while how this is done by taking a very simple example. But roughly this is what happens. So we will have a data path and we will have a control path. So any circuit will have a data path and a control path. So data path, control path. So that the loop structure, so based on what you have in the loop, you will have the data path get synthesized, and there is a control path or a control plane which schedules the multiple iterations onto the given data path across clock cycles. This is what it is. So I will take a pause here and see if you have any questions. Any questions you would like to ask at this time? Doing all right?
Sir, how do we distinguish the variables whether they are stored in BRAM or DRAM?
I think there is some kind of implicit understanding, or the manual says if you declare it in a kernel, it will be stored in the memory will be allocated on the VRAM. And I think there are some pragmas which will kind of tell you where you should be storing your array also. That we may talk in at a different point. But at this point, the simple answer is, yeah. So the way this whole thing is structured, yeah, it's the ints are all. In the HLS module, I looked at a different example. So there they have a different story, but I think in this story, the on line number 54, at least for sure, what we know is, V1 underscore buffer is stored on the VRAM of the FPGA. Okay.
Sir, one doubt.
Yeah, just a minute.
Like how like the data transfer from the block RAM to the SRAM, is it faster compared to data reading from directly block RAM and then executing?
Can you repeat again? Block RAM to SRAM.
So here we are transferring data from our block RAM to the SRAM inside for one vector addition.
No. Wait. We are transferring data from DDR global memory to the local memory.
Okay, so is it that, do we have any benefit of doing that? Because then we are transferring two times. If we directly read from the global memory, we don't need this read one loop. So how is it helping in latency? Because
let me see. 1 minute, Tanmay. Let me see if your question. I'll set up the thing for you. CPU, FPGA. So initially what we did is, maybe Padmini ma'am can help us here if we have, I'm not getting it right. So here what we initially did is we did the transfer of data, the vectors A comma B from the DDR memory of host to the device. Are you with me here, Tanmay?
Yes.
And then on line number, the read loop, this V1 underscore buffer, it is allocated memory here. And what we are doing in line number 64 to 67 is we are taking a chunk of data from here and moving it here. And we are VRAM is definitely faster. Accessing VRAM is definitely faster than accessing the global DDR RAM. In fact, the strategy usually is there is the strategy when we design system is so here we are not seeing much benefit. The key mantra that you have to remember is maximize data reuse. Data not use, data reuse. Once we bring data to the FPGA, we should use it as much as we can because our goal is to minimize the main memory traffic to the DRAM. So the mantra here is we want to maximize the data reuse, or we put it in another way, we want to maximize different word is maximize compute intensity. That is, compute intensity is number of operations per byte of data or per unit of data, per byte of data fetched. So because the speed at which the FPGA can do computations is way higher than the speed at which the memory can feed. So because of that, if there is a lot of reading of the DDR memory is there, then the computations, there will be a lot of stalls in your hardware circuit. So these two ideas are important. One is maximize data reuse. How do you maximize compute intensity? That is the number of operations per byte of data. It is by doing the maximizing the data reuse. But right now, in this particular case, we are not. We are getting the data from DDR RAM to VRAM, but no, but we are not saving much beyond that. Did I answer your question, Tanmay, or?
Yes, like I was confused. Why are we transferring it to RAM? Because we can directly read from global memory.
So in this particular case, we are not using it. I think there could be some other reasons in order to reduce. I'm not sure. There could be some other reasons to bring data here, but we are not exploiting the fact. But generally speaking, moving data from DRAM to VRAM and working on it as much as you could is the best strategy.
Right. So I can add a little bit here.
Yeah, sure, please. Yeah.
So the FPGA that you use, right, for any accelerator, it actually has what we call a shell, which is created. Okay. And that consists of IP to do basically communication from the host and also to read from DDR. Right? And when and then basically there is a runtime library, which is a layer below OpenCL. So every piece of hardware that supports OpenCL has to implement those runtime functions. Okay. And the runtime functions take care of things like, setting up operations, setting up transfer of data, you're moving instructions to the command queue and things like that. Exactly how it is done for the specific hardware will be taken care of by that runtime layer. Okay. So, depending on the FPGA that you use, right, and the platform that you use, you may not have access to the host memory directly, right? Or it may be slow because I will basically communicate to the host through PCIe, right? And the data still has to come from somewhere, right? So the CPU has to, know which address to put the data to and so on. So it's not that there is a dedicated connection for data coming from the memory of the CPU directly to the FPGA, right? It still has to come through the host over PCI.
Okay. Okay, so data transfer here is the most costly operation. So we are doing this to prevent.
It's costly, yes. So, and the more you do data transfer, from the host side, right? That is the most expensive operation. So ideally, the best way to parallelize is, you take the data which you know is sitting on the CPU host and you transfer as quickly as possible to the DRAM which is sitting on the accelerator board. Right? Whatever it is, it will still be faster for the FPGA to get data from that DRAM rather than from the host memory.
So, Padmini, so one particular question, I think Tanmay's question, which Prithvi also partially answered, I guess, is in this particular code example, what is happening is there are in1 and in2 or two input vectors. Okay.
Right, right.
And part of in1, we are bringing it to DRAM. Okay. By into the buffer v1 underscore buffer declared on line 54. So yeah, and then yeah, we are doing the computation. So what is the, why can't we directly, why are we doing this? Why can't we have a very simple code? Like, so we might have something like, I'm just writing my dummy code here for vanilla code. Is you just write, for I is equal to 0, I less than whatever size, plus I. This is out. Yeah, so out underscore R of I is equal to in1. Yeah, so yeah, that's it. In1 I plus. Why can't we do this? Okay, because is there any disadvantage or between these two codes? This is the vanilla code versus the code that is given here. Do you see whether there is an advantage in buffering? Why can't we write this code?
So when you write vanilla code like this, how does the accelerator know where to store in1 and in2? Right? As far as the accelerator is concerned, in1 and in2 are some pointers to global memory, right? Or some pointers to a memory somewhere. Right?
In the devices global memory, in1 and in2, as per the semantics.
Yeah, so we have already set it up, right?
Yeah, that's true.
That's right. But then, so the thing is, so the way OpenCL is set up actually is you need to be able to bring in the data here for the accelerator to compute it, right?
Okay.
So where will the accelerator get the data from, right? So my accelerator has to understand that I am taking the data and I'm bringing it in somewhere. See, because your adder does not sit in the memory, right? My adder sits on the FPGA. So when I'm writing a kernel, somewhere I have to physically bring the data from the memory into the FPGA, add it and then send it out, right?
No, it's already done. I think, see, it is already.
Maybe I missed some context in the
Yeah,
program.
I think so. What is happening
Has it already been done?
in vr.cpp, now when we are in the kernel in1, into the data is already transferred to the FPGA's DRAM. And in fact, if you ignore my code from 56 to 59, the 69 to 71. So this is the place where we are reading the data in1, that is from FPGA DRAM to v1 underscore buffer.
Yes, which is the buffer that sits on the FPGA, correct?
On the FPGA. The question is, and then if you go down, if you see this, the last part, yeah, so the lines 76 to 80, this is the place where we are
Oh, I
reading.
see, I see. So the question is instead of V1 buffer here, can I not do in1 directly?
In one.
Yes.
Yes. Okay. I'm sorry. I misunderstood the question. Yes, there is no reason why you cannot do it that way. I think the goal of this program also is to show that you can actually bring in data to allocate to a buffer.
Yeah.
See, if you wanted to do a more complex operation, right? Let's say you want to do a matrix multiplication, or you want to do some processing on an image, then you would actually, it would not make sense. It may sometimes make sense to work on directly on memory. So in the zero copy type of setup. But sometimes, it may not make sense. So you may want to actually bring it in, process something on the FPGA. So this is really, think of it as an example of how to, set up local memory on the FPGA, not necessarily the most optimal way to do it.
Yeah. Good. Yeah, that makes sense.
Does that make sense?
Yeah. Makes sense.
Okay, so like here it's just like optional that we are transferring it. Like we can do another V2 buffers and replace this
Yes,
IN2 also.
absolutely.
Okay.
Nothing prevents you from doing that. See, so if you see that is why this the third loop, the one we add write C, right? That function is basically, it is showing how you can do it in two ways. Right? So you burst write it to global memory through this outar I plus j, and that the compiler will take care of scheduling through the shell, right? So the shell takes care of how you read and write from DDR. It has memory controllers in it. And this is telling you that you can basically do something, you can do work with some data which is in the local memory on the FPGA, and you can also work with data which is in the global memory. Right? But what is hidden here, right, is the fact that there is a latency. Now, it will be much faster for you to bring in V1 buffer. It will be faster for the adder to add the data in V1 buffer, right, than it will be to access the data into I plus j, because the memory controller still has to bring that data in and keep it somewhere. The compiler takes care of it for you, but it has to bring it in and keep it somewhere, right?
Okay, I understand. But then we have to transfer outar and IN2 also to like match the latency, because if IN2 is slow and outar is slow, then we do this. Like then it is no point.
Correct. So when you actually do the application, you will have to, match and you'll have to figure out what you want to do, how you want to pipeline your application. So how will you bring the data in accordingly? That's a very important part of the design. Am I making sense? Did it answer your question?
Yes. Like this was just an example. It's not the most optimal.
Yes. It is an example. And I think there is a lot of traffic on the chat also about how much memory you have. So Sampath's point is correct. So memory inside the FPGA is limited. That's correct. But the point is that the memory, if whatever you put in the memory inside the FPGA can be accessed very quickly, right? So if you wanted to parallelize, actually, you would bring memory to the FPGA, run a lot of kernels and do computation on that. And in parallel, right, transfer more data from the DRAM to the FPGA, because that is time consuming.
But in that case, ma'am, it's like we are already we already know what kind of device we will be using, and based on that, we are trying to make this code. It will not be a generic code, right? It's not a generic code.
That's right. Absolutely right. So you will have to know how much local memory you have on your device. You'll have to know, what is in the DRAM, what is the size of, the data that you're dealing with. And that is why this design is a little different from just directly designing a software program, right? If I was just writing C code to do this, I wouldn't think about where data is stored. Right? But here you actually have to think, because every operation is expensive. So even though you can write your code like this, ultimately for the adder to work, into has to be brought in, right? And outar is, the result is stored in somewhere on the FPGA and then transferred to the DDR in a burst. Makes sense?
But
Yes,
here the
ma'am.
reading writing is not happening in parallel, like it is happening sequential. So is there a way to make it like this writing from like the global to the local FPGA memory? This is not parallel. So how will we be sure that this will happen in parallel with this? Will the compiler take care of it?
What do you mean by it's not parallel?
What I mean to say is like this will happen um, like when we run this loop, will it run sequentially or this read operation will happen before like some parallelism is applied here?
So maybe I can see, Tanmay will take a very detailed look at this question later. But
Okay.
a quick answer I will give is, let me
Ma'am,
see.
I have a query, ma'am. Can I conclude to a statement? I'll ask you in Intel's context. Can I conclude that Avalon MM is slower than Avalon Stream? Can I ask you in that way? Can I conclude a statement such? Means generally from DDR to local memory, the transfer is through Avalon MM, memory mapped, right? And from the transfers from local to local will be in Avalon Stream. So can I come up, can I say that, of course, they will say that the local transactions are faster. Means, is it always the case?
It depends on how you set it up, right? So are you doing DMA through a controller or whatever? In general, good rule of thumb is to say that yes, my accelerator will be able to access local memory the fastest.
Yes, ma'am.
And then global memory at the next level, and then memory, anything which is in the host memory will be the slowest. It's just
Yes,
a rule of thumb, just like your caches, right?
Yes, ma'am. Yes. Come, understood, ma'am.
Yeah, you can think of it as some kind of cache hierarchy.
Okay. Okay, fine. Means it will be always the case, right? Then most probably in every case it will be like that.
In general, yes. Now, sometimes, if you are depending again, right? This depends on how you set the hardware up. Maybe you can set up very fast DMA, then depending on how it is set up, I would say it is generally true. It is generally true.
Okay, ma'am. Fast DMA means increasing the clock frequency of the hard IP. Is it like
Yes,
that?
exactly. So then it depends, right? It depends on the speed at which your kernel runs, the speed at which your DMA is able to run, how much space you have to store everything.
Okay, ma'am. Thank you.
Sahiti's question, is it buffer size? Is it like buffer size is a limit due to size of VRAM? That is true. So I will give quick 2-minute answer to your question, and then I will take this question again later. So in the loop that we have, so you can think of this as this loop have a structure read. There is a read that is there, and then there is a compute, and then there is a write that happens. This read could be from DRAM to VRAM, and this compute is happening within VRAM, and this write is happening from VRAM to DRAM. This could be the typical structure for many designs that you see. Okay, typical structure. And so what happens is the iterations, let's say the iterations, there is an iteration I, which 0, 1, 2, 3 these iterations. So one way of looking at this is, so there is a read 0. I will just use R0 for read. Oh, how can I do? Okay. So we can do, so there is an R0 happens, compute 0 and write 0, R0, C0, write 0, like that it happens, so on and so forth like this. So here if you see, the while the FPGA is kind of busy only when it is doing during the C0 only during the C0, C1, C2, only during compute cycles. But when read is happening or write is happening, then what happens is it is simply waiting. So stalls when reads are happening, whatever or writes. So these are stalls, clock cycles. You are not doing any compute in the in these cycles. So this is a bad thing. So read R0, R1, all these things, read and write phases. Your FPGA hardware is not doing any useful stuff. So usually we want to kind of come up with ways so that the multiple iterations will overlap with each other. So at least to some extent, what happens is R2, C2. This is W2, R3, C2, W3, so on and so forth. We want to overlap, so compute with the read operations. That is, while you are doing compute for iteration 1, you are trying to do a read operation for iteration 2, and you are doing the write operation for iteration 0. So by kind of cleverly designing your whole system like this, what happens is so you will be able to keep eliminate the stall cycles and keep the FPGA circuit busy all the time. So in order to kind of come up with a kind of, if you see, there is you will see that there will be some kind of overlap between like for example, if C1 and R2 are overlapping, so if C1 is doing computation and if the input buffers are manipulated, then the data gets overwritten. So in order to solve these kinds of problems, we use techniques called as double buffering or ping pong buffers, etc. So these are the architectural approaches that you use to keep your CPU busy. So you bring the data from DRAM to VRAM and do compute, and you do the write. If you're not clever in your design, most of the time your system is idle, it is stalling. But on the contrary, no, you have to modify your design in such a way so that no iteration I0, the consecutive iterations overlap with each other. And in order to do it, the compiler doesn't do it for you automatically. You have to work hard towards it. Some things it does, but many things it doesn't do. So you have to kind of explicitly introduce these double buffers at the read stage and the write stage. And these techniques are very, very common, and these are the kinds of things we will be doing when you're working with complex problems. And the challenge here is this kind of matching. I kind of wrote nicely so that no C1, W0, and R2 as if they are of the same amount of work. But depending upon the buffer size and the kind of computations that are happening in the core in this loop, no, we have to match these sizes. Otherwise, you can have a small small compute time, and then you can have a large read. So what happens is lot of time, no, you will still see stalls. So you have to balance these things, and these are the things which we will study later. But this is a quick answer to Tanmay's question that no, are we doing sequentially? What is the benefit, and why don't we do parallelly? Yes. So does this make sense, guys? Just want to check with all of you, or you all with me on this example. This is a template code you will see, and no, and we have to optimize it.
Sir?
Yeah.
Sir, from left to right, like this, read, compute, and write. is this being mapped in this pipeline way, or this
No,
the
let's not
code?
get. Let's look at it at a conceptually. We will.
Okay.
Time is 1:30. We will kind of stop here. Just want to check. Can you see a raise of hands on whether you understood the last idea at a block level, at what we are trying to do? So we will take a pause. We'll stop here for today's lecture, and we will continue in the next.
Hello, sir.
Yeah.
So one last doubt. So here we have 3 instructions in each one of the for loops, right? So
They are not instructions. They are more than instructions. They are blocks of instructions.
yeah. So in the vanilla code that you wrote earlier, when that code, like that code is also valid, right? So when it gets compiled, all like when we're directly accessing the DRAM memory, so that the compiler will handle and make it a separate read instruction and then a separate compute instruction and a separate write instruction, right?
Yeah, that's true. Okay.
Okay.
Yeah.
Thank you, sir.
Okay. Yeah, let's stop here. Thank you all. So, couple of announcements. You will have a next Wednesday class. You will have a small quiz, I think, for 45 minutes. And whatever we have discussed so far, and whatever the material that we have posted on the course website, that will be there. Yeah, so take it easy. The intent of the quiz is, so that you will kind of